Hello there. This is Rafin again. This will be our lecture number 2. So if you look at the syllabus, you'll see that in the module 1, which is Introduction to Energy Conversion, we have 2 lectures. Both of them are review classes, you can say. The first lecture was on the review of basic electrical engineering. So I wrote it like this: review of basic electricity, and the experiment number was 008. For this lecture, we'll be talking about fundamentals of magnetic circuit, and I denoted it as the experiment 00B because practically this is not the actual experiment that we are gonna do. From next class, we will be seeing the actual experiment. So, why, you may ask? Because we have to actually be synchronized with the class. You need to have some basic understanding of um, transformers, like electrical machines, transformer motors, and the principle of magnetism, and uh, Faraday's law of electromagnetic induction, mutual coupling, mutual inductance. So these sorts of things, these are very basic stuff that are required for you to actually understand how a transformer works or any other machine works. That's why the first 2 classes are important. In your actual course, you will actually get the um, extended idea of the review of those theories like basic electricity and fundamentals of magnetic circuits. So I'm not gonna actually uh, uh, do any experiments without having you have those ideas. So this is the lecture number 2. So I will be uploading it in a very short period of time. So you will see here lecture 2. I haven't actually uploaded it yet. So I'll upload once I'm done with the recording. Uh, yeah, so if you look at the lecture 2, um, it's based on fundamentals of magnetic circuit. So I have actually uploaded a couple of video resources. I'll talk about this a bit later. Let's talk about video resources. You will have this video here. Other than that, you have the basic videos regarding electromagnetics, eddy current, Lorentz force, right and left hand rules, electromotive force, that is EMF, uh, then voltage, current, uh, electricity, magnetism. Uh, in this video, you'll also get some idea about magnetomotive force also. So in upcoming lectures, not this one. And we have a simplified magnetic circuit. The basic concept I have uploaded this one just to actually give you an update or review, I'd say, on the magnetic circuit concept. And then magnetic circuit example 1, a numerical problem will be there, and you'll see that. And then the fundamental, this is the most crucial law that you need to know um, in order to understand how electrical machines work. So this is Faraday's law of electromagnetic induction, which is very important. I cannot stress enough about this one. And finally, you have Lenz's law. So I'm not going to extend this lecture too much. Let's see what magnetic circuit is. This one. Let's have.
So in today's video, we are going to learn the basic concepts of magnetic circuits. Now a magnetic circuit is made up of a closed path to which a magnetic field, represented as lines of magnetic flux, is confined. Now let's consider this magnetic circuit composed of an iron core and an air gap. Now in place of this iron core, we can have any material of high magnetic permeability, so that can be a steel and so on and so forth. Now, considering this circuit, we have a coil of n number of things wound around the iron core, and let's assume that we have a voltage source, that is a DC voltage source, in between the core. Now this voltage source is going to drive current, say I, through the core, and thus generating magnetic field around the core, which sets up magnetic flux within the magnetic circuit. Now this magnetic flux flows through the iron core as well as the air gap. Now let's focus on the electric equivalence of this circuit. So here we have a voltage source V that is driving current Ci through the circuit, and the resistance of this circuit is made up of the resistance as a result of the air gap as well as the resistance as a result of the iron core. So we know that the applied voltage or the source voltage is giving us the current that flows through the circuit times the total resistance, that is according to Ohm's law, and that is equal to multiplying I across, then you have I times Ra plus I times Rc, and thus the voltages dropped across the circuit is equal to the source or the applied voltage according to KVL. And if you want to find the current flowing through the circuit, then that is equal to the applied voltage divided by the total resistance. Now coming back to the magnetic circuit, the force or the source that drives magnetic flux within the circuit is called the magnetomotive force, which is represented as MMF. And then within the magnetic circuit, we have two resistances, that is the resistance as a result of the air gap as well as the resistance as a result of the iron core. Now in a magnetic circuit, we call this resistance the reluctance. So in actual sense, we have Ra to be the reluctance of the air gap, and then Rc to be the reluctance of the iron core. Now the iron in this case has a high magnetic permeability, which means that it has a high ability to set up magnetic flux within itself, and hence has a very low reluctance as compared to the air gap, which has a high reluctance and a low magnetic permeability. Now given a magnetic circuit, in this case, the magnetomotive force, or better still the MMF, that drives magnetic flux within the circuit is given by F, which is equal to the current in the core times the number of turns of the core, and that is measured in amperes, or better still ampere turns. Now as the flux flows through the magnetic circuit, a magnetic potential drop is developed across each section of the circuit, and if the circuit is homogeneous and thus has uniform cross section, then what this primarily means is that the magnetomotive force, or better still the MMF per meter length of this magnetic circuit, is said to be the magnetic field intensity, and that is represented as H, and that is equal to the magnetomotive force divided by the length of the magnetic circuit, and that is measured in amperes per meter or ampere turns per meter. Now we also have what we call the magnetic flux density, which is equal to the magnetic flux divided by the cross-sectional area, also measured in Webers per meter square. And then this magnetic flux density is somehow related to the magnetic field intensity by this formula, that is B equals mu naught times H. And then we can use this formula to find either B or H, especially when we are dealing with non-magnetic materials, or better still free space or vacuum. Now in the case where you want to find the value of either B or H for a magnetic material, we can't use this formula, hence it is advisable to use the BH curve to find either B or H when one of them is known. Now the reluctance of this circuit is giving us L divided by mu naught mu R A, where L is the length of the magnetic circuit and then A is the cross-sectional area, and then the reluctance of the magnetic circuit is measured in ampere-turns per Weber. And then considering this circuit, now the reluctance as a result of the air gap is given as L over mu naught A, while the reluctance as a result of the iron core is given as L over mu naught mu R times A. Now from Ohm's law, we know that the source voltage is equal to the current times the total resistance for the circuit. That is considering an electrical circuit. Now in the case of a magnetic circuit, the magnetomotive force F is equal to the magnetic flux times the total reluctance. In this circuit, we have the total reluctance composed of the reluctance as a result of the air gap and the reluctance as a result of the magnetic core, or better still, the iron core. Now, if you should multiply the flux by Ra and then Rc, then you are going to get flux times Ra plus flux times Rc. And that becomes the magnetic potential drop as a result of the air gap plus the magnetic potential drop as a result of the iron core. Now, if you should add these two values, then that should be equal to the magnetomotive force. Now, what do you think will be the inverse of the reluctance? Now, the inverse of the reluctance is called the permeance, and that is equal to mu naught mu R times A divided by L. And this permeance is defined as the measure of the ability of a material to permit the setting up of magnetic flux. So in summary, in an electric circuit, we have the source to be the EMF, that is electromotive force, and then represented as V, and that is equal to the current flowing in the circuit times the resistance of the circuit. Now in a magnetic circuit, we call the source the magnetomotive force, and that is represented as F and given as I times N, and that is measured in amperes or ampere-turns, and that is also equal to the magnetic flux times the reluctance of the circuit. Now the current in an electric circuit, that is represented as I, is measured in amperes, and then in a magnetic circuit, we call that the magnetic flux, and that is measured in Webers. Also in an electric circuit, the opposition offered to the flow of current is called the resistance, that is represented as R and then measured in ohms. Inside of a magnetic circuit, we call that the reluctance, that is the opposition offered to the flow of magnetic flux, that is also represented as R and is measured in ampere-turns per Webers. The conductance in an electric circuit, which is represented by G and then measured in Siemens, is called the permeance in a magnetic circuit, that is also represented by A, and that is measured in Webers per ampere-turns. So that's it for today's video. Thanks for watching and see you in my next video.
So that is the video I have uploaded to. It's a very simple, basic magnetic circuit video. So I hope it will help you to understand. Then I have uploaded another one as I've mentioned, and this is the super important topic, which is Faraday's law of electromagnetic induction. I hope if you go through each of the videos, it will help you immensely to grasp the idea of magnetism and fundamentals of magnetic circuit. So since in this lab, we are not going to experiment anything. So let's start by simulating something. So I have actually uploaded one Simulink file here, which is for a solenoid. So you can actually download this one. So if you download it, and if you have MATLAB installed, you just need to click on it. You will see the file. Now Okay, let's talk about this, the concept of it. So the concept is to have a like solenoid circuit, which will look like this, and another I which is connected to a like owned in a what is it called, a core, iron core, and we have another iron type material which is called the mover here, and which is connected to a spring. This is a spring which is connected to a wall. So if we actually apply some DC voltage here, so DC current will circulate around this solenoid, and there will be a flux surrounding this place, and it will try to attract this. So there will be some force, like that is attracting the mover towards the stator, and this is the stator, and this is the mover part. So there will be some attraction, so the spring will feel some force, and if we cut this line, so this mover will go back to its original position. So that's all. So you'll have to actually simulate this one. Let's see whether it opened or not. Let's open one more time. I'll have to share again. I don't know why it is not opening. We try another way. I don't know what is going on. It is not let this. Okay, I managed to open it. I don't know what happened. It got hanged. My laptop got hanged. Anyway, so this is the solenoid example that I've talked about. So if you look at this model, you don't have to do much work. So all you have to do is run the model and see the scopes, like this solenoid position scope. That means like oscilloscope type of thing, where we can see the end result output waveform or anything. So if you look on the left side, we have a DC voltage source having 50 volts. If we double click on it, it will give us a constant voltage of 50 volts. We can change the value. I'd like you to actually change the value and see what's going on. And we have a switch here, which is controlled by this energizer. If we double click on it, we'll see there is a step function um, there. If you want to change the switching time, like if you want to switch it after some time, like for instance, 3 seconds or 4 seconds, you can actually uh, control it by these functions. And we have this solenoid block, where this is the solenoid electromagnetic converter we have. That means this is the solenoid we're talking about. We have magnetic core representation, which is the reluctance that we saw in the previous section. We have like cores, magnetic core, reluctance of the magnetic core, and reluctance of the air gap. So we have that, and the mover section, that's the mover section. So from this circuit we can actually get the positioning how much the position got deviated from its original position, we can actually measure it from this circuit. So that's that, and that's the load force of the spring. So that's the force input. So this is also a step function, so we can change it. The force of the spring, we can actually manipulate it. If I run it, if I click run here, it will compile, then it will actually execute the whole setup. So it's done. If we click here, double click here, it takes some time. We can see the solenoid position from 5,000 millimeters to 0. So it came towards the core. So after some time, after 2.2 seconds. So total, it was simulated for 0.5 seconds. So after starting, the initial position of the not solenoid, the mover was uh, 500 uh, millimeters away from the core, and at 1 second it got energized and this switch got closed. So this current from this voltage source could go to the solenoid and energize the solenoid and have a magnetic field around it and becomes a electromagnet sorts of thing. So the core tries to attract, and within 0.1 second it manages to bring that mover block to its near the core. So that's the experiment. Now there is another thing. So if you click here, the first one, plot position and flux, you will see position and magnetic flux information here also. So there are other MATLAB what is it called, models similar to this one, which you can actually get from the internet. This is one of the examples, very basic examples. So I'd like you to actually run this, manipulate the voltage, like change the voltage to see, change the force magnitude, and or force at which time the force will be reacted. You can change those timings just to see how it works. So I I'd like you to actually play with it, and then after that I'd like you to actually write a report on whatever you have learned from this. So there will be two-part assignment. One will be on basic question answer related to not electrical, magnetic circuit, and second part will be based on this one. Whatever you have learned so far, you can actually include the plots here given, and these two plots you can definitely include. You could write you could write what have you learned so far. I will actually mention what are the things that needs to be included in the lab report. So that will be a two-part lab report. I think that's all for today. So from next week, we'll actually learn how to experiment, learn how to use different electrical machines. So that's all for. And if you have any questions, please feel free to contact me. If you don't understand how this works or how anything works related to electrical energy conversion, this course, you can email me at any time. We can have a live Zoom session if you want. So that's that. Um, have a nice weekend. Thank you.